Alright, so in this video we go over section 5.1, which is polynomial functions and models. So in this section we are going to identify what a polynomial function is and their degrees, identify the real zeros of a polynomial and their multiplicity, and analyze graph of a polynomial function. Alright, so let's identify a polynomial function first and their degrees. So the general form of a polynomial function is as follows: f of x n, a sub n x to the n plus a sub n minus 1 times x to the n minus 1 dot dot dot, many terms, and then a sub 1x plus a naught, where these a's with subindex n and minus 1, 1, 0, etc. are the coefficients, are real numbers, are constants, and they're coefficients of the polynomial. And n, it is very important that n is strictly 0 or greater than 0. Note that it means no negatives, and has to be an integer, therefore also not rationals. Okay, not rationals. Okay, and well, if a sub n is not equal to 0, then that's the leading coefficient, this number right here, the leading coefficient, which is the coefficient that multiplies x to the highest power, and n is the degree. So we are going to identify a few with the examples below. So determine whether each of the following are polynomial function, and for those that are not, that are, state the degree. For those that are not, explain why not. So in this case, first one is it's a polynomial function. Okay, so yes, and the degree, is 5. It's a fifth degree polynomial. Letter B, let's have a look at this. Well, I'm missing an equal sign here. So in this case, I would rewrite g of x as x to the 1/2. So in this case, it's not a polynomial. Because the degree is not integer. In fact, this is a radical function. That's what it is. Letter H. This is not polynomial. This is in fact a rational function, which is the quotient between two polynomials, actually. So that's why this is not a polynomial function. Okay, so let's look at the next one, letter D, f of x equals 0. Well, even though it doesn't have any x's, right? I claim this is a polynomial because this is the same as saying 0 x to the 0 power. Because what is x to the 0? X to the 0 is 1, and 0 times 1 equals 0, which is what we had at the beginning. So in fact, this is called the zero polynomial. G of x equals 5. Alright, let's have a look at this one. This is also the same as saying 5x to the 0 power. So the degree is 0. Again, if we look at the definition, the degree can be 0 or greater as long as it's an integer. So yes, degree zero. Letter H. For letter H, we might need to do a little bit of work before we can determine whether it is or whether it is not. So what I'm going to do, I'm going to expand the binomial, and then I'm going to distribute the negative 2x to the 4th power. So this is x squared plus 6x plus 9. All right. And when I distribute every single, when I distribute the negative 2x to the 4th through every single term inside of the parentheses, what we get is 2x to the 6th, negative 2x to the 6th, minus 12x to the 5th, minus 18x to the 4th. And yes, this is a polynomial. Degree 6, because 6 is the highest power, and in fact it's an integer that meets the condition. So let's see what's next. So now let's look at power function. So power function, it's the power function of degree, and it's a monomial function of the form f of x equals ax to the n. And again, same conditions. A cannot be 0, and n it's actually a number greater than 0. It's an integer greater than 0. Again, a is the leading coefficient and n is the degree. So in this case, for power functions, we are going to have two different. Let me see if I can highlight this, because unfortunately I ran out of ink over here, and I wasn't able to print this page in color. So we're going to look at some properties of this. Oh, it didn't help. Properties of these functions. Okay, so in this case, it would be a good idea to split two cases of the power function, that in which n equals even and n equals odd. So we're gonna have power functions with even powers, like x squared, x to the 4th, x to the 6th, x to the 8th, x to the 10th, etc., etc. And likewise, we are gonna have power functions in which n is odd, such as x to the 1st, x cubed, x to the 5th, x to the 7th, x to the 9th, etc. What are those properties? So when we have a power function whose degree it's an even number, we're going to find out that the function it's an even function. You know, it's symmetric with respect to the y-axis, that is connecting with the material we covered in the preceding chapters. The domain of these functions are all real numbers, and the range is the set of all non-negative real numbers. That is, this is a fancy way to say y belongs to 0 all the way to infinity. Non-negative, it's all positive numbers including 0. The graph always contains the points negative 1, 1, 0, 0, and 1, 1. And as the exponent n increases in magnitude, the function increases more rapidly when x is less than negative 1 or x greater than 1. But when we get closer to the origin, the graph tends to flatten and lie exactly, or right actually closer to the x-axis. So we're gonna use our graphing calculator to have a look at this. Let me fix the focus here. All right. Yes. So let's use a graphing utility to graph the following power function and explore the properties mentioned above. So I'm gonna go here and click y equals. If you have anything, be sure to clear, and I'm gonna type x raised to the second x raised to the fourth and x raised to the sixth. So only these three. And I'm going to click graph. So we're going to have x squared, which is the parabola, x to the 4, which is not quite like a parabola, and x to the 6, which is not quite, as you can tell here, well, after x equals 1, the graph starts increasing more steeply, right? And then let's look at the other properties. So according to the guidelines here, so I'm gonna hit second table. The point -1, 1 is always there, the origin is always there, and the point 1, 1 is always there for all of them. All right, so now let's look again at the graphs. Let's look at the graph. So what happens for larger values of positive x? So for larger values of x, the graph goes all the way up to positive infinity. For values that are negative and big, also goes to positive infinity. This is what we call the end behavior, in which we are going to we're going to analyze this in more detail later in the section. Now let's look at the case in which the power function has an odd power. Okay, I should have changed this for odd, positive odd integer. Okay, now let's see. F is an odd function, that's to begin with, which means that the function, that its graph will be symmetric to the origin. In this case, the domain and the range will be the set of all real numbers. The graph will always contain the -1, -1, the origin, and 1, 1. And same as the exponent n increases in magnitude, the function increases more rapidly. And you could see that on the previous example, how the numbers became bigger and bigger. You know, like for x squared, -9 squared is 81, but -9 cubed, look at how big this number is. I mean, to the 4, look how big this number is. -9 to the 6th power, look how big that number is. So the numbers start getting bigger more rapidly for higher powers. And again, it gets more steep for x greater than 1 and less than -1, and gets flatter actually as we get closer to the origin. So I'm going to do the same. I'm going to do these explorations here. So I'm going to go y. I'm going to change the exponents to a 3, to a 5, and 7. And I'm going to hit graph. That's one. See how those graphs are symmetric about the origin? Can you recall the criteria for that, right? So that's what we have for. So now in this case, for the end behavior, for as we get x equals infinity, the graph goes to positive infinity. But in this case, as opposed to the previous case in which the power, the degree, the power is negative, if we go negative infinity, the y values are going to go to negative infinity, not going to go up to positive infinity like the previous case. All right, now let's identify the zeros of a polynomial. For example, let's see. Okay, let's see what are we going to have here. So this is how in general the graph of a polynomial is going to look like. Let me actually draw it because I ran out of ink. Okay, so these graphs are gonna have ups, downs, max and mins, turning points, different with all these characteristics in a very in a very similar way for every single one of them. Now, what's the most important aspect here? In this case, it's going to be the intercepts. More in particular, the x-intercepts, or because those are going to be the zeros of the function. That's another way, another name we're going to give to this x-intercepts. Now, the core part of this is that if a polynomial can be factored completely, then we can easily locate the x-intercepts of the graph by solving the equation and using the zero properties. For example, let me give you one. Let me give this this example. Well, in this case, it's already factored. It's already factored, so we don't need. They're not giving us polynomial. So here, what we get is that if we set x minus 3 squared times x plus 1 equals to 0. Well, in this case, this is the same as saying x minus 3 times itself. That means that we can set x minus 3 equals to 0. Well, in this case, notice I have a repeated. I don't have to do it again. And I'm going to do only x plus 1 equals to 0, which means x equals to 3 and x equals to negative 1. So these are the x-intercepts. And these are also the zeros of the polynomial. And the reason for which these are called the zeros of the polynomial, it's because if I get back to plug them in, for example, if I do f of 3, that's going to be 3 minus 3 squared, 3 plus 1. I'm going to get 0 squared times 3 plus 1, which is 4. But in this case, this is going to be 0 times 4, which equals 0. All right? That's again going back to the zero product property. We get the values of x for which the given polynomial is 0. And likewise for x equals negative 1, plug in negative 1, we get minus 3 squared plus 1. We get negative 1 minus 3, negative 1 plus 1. So this will be negative 1 minus 3, that's a negative 4 squared times 0. So this is 16 times 0, which is 0. Okay, so the solutions to the equation f of x equals 0 are the intercepts, are the x-intercepts of the graph of this described by this polynomial, and these values are also the zeros of the polynomial, because those are the values that when I plug them in, I get a y value of 0. So let's go over a definition here. So if f is a function and r is a real number for which f of r equals 0, then r is called a real 0, which is what we were talking about a few seconds ago. It's a real 0. It's a solution to the equation, and it's a 0. As a consequence of this definition, that we are going to have these 4 statements right here. Number 1, the number 1 statement is r is a real 0 of the polynomial, which is what we already said. And then in the next place we have that where's my highlighters? There's another one here. R is an intercept. It's an x-intercept of the graph of f. And then x minus r is a factor. It's one of the factors of r. And finally, r is a solution to the equation f of x equals 0. So those four statements are going to be true about r's that come from the polynomial. Okay? So in summary, well, the real zeros of a polynomial function are the x-intercepts of the graph and are found by solving the equation f of x equals 0. This is the very core of this chapter. This is what we are going to be doing for the rest of our life, for the rest of the, not our life, at least for the rest of the chapter. That's why I'm using this gold marker, because this is the very gold. Alright, in fact, these were supposed to be printed in grid, but for some reason, because my printer was running out of ink, came out in gold color, so you can take that idea. Okay, now what's next? Let's put this in action. So find a polynomial function of degree 3 whose zeros are -3, 2, and 5. Use a graphing utility to verify your result. All right. So let's see. So we are going to have 3 zeros, but I'm going to label them. I'm going to label them as R1, which is -3, R2, which is 2, and R3, which is 5. Okay. As a consequence of these zeros, x minus r is going to be a factor of f. That means x minus r is one of the factors. X minus r, which is x minus -3. That's one of the factors, which equals x plus 3. That's one of the factors. X minus r2 is going to be another factor. X minus r3 is going to be another factor. So in this case, x minus 2 and x minus 5. Now we are going to form this f of x, f of x equals x. Actually, I need to add an a. This a will be the a that is always there, the leading coefficient. I'm going to talk about that in a minute. X minus r1, x minus r2, x minus r3. So that's going to be the general form for this polynomial that we are going to form with these 3 zeros. A times x plus 3, x minus 2, and x minus 5. Alright, but what about that a? Okay, what about that a? So you might remember from the previous chapter that this a means a vertical stretching or shrinking. And if you recall, a vertical stretching or shrinking doesn't have any effect on the x-intercepts of a polynomial, of a function. You might remember that we did an exercise. It was on the video lecture, and it was on a homework as well, in which we determined that this value of a doesn't change anything. So let's look at the easiest case. For a equals 1, let's do the easiest one. Well, we don't need to write anything out. So f of x will be 1 times x minus x plus 3, x minus 2, and x minus 5. So I'm going to go to the graphing calculator to show you how this is going to look like. So in this case, let me go to y, clear everything we have, and I'm going to use y1 for the polynomial. So I'm gonna have parentheses x plus 3, close parentheses, open parentheses, x minus 2, close parentheses, x minus 5, close parentheses. Oops, I forgot to insert parentheses. There we go. Oh, what the hell? I clicked the clear instead of the graph. So let me start again. So x plus 3, x minus 2, x minus 5. Graph. Yes, not clear. Graph. So we are going to have a polynomial function. It has an up and down. All right, it has an up and down. And there is here we can see the 3 zeros. One of them is -3, the other one is 2, the other one is 5, as we can tell here from the graph. Now let's add a constant other than 1 and see if that has any effect. Second ints, I'm gonna do 2, for example. Actually 3. Let's make it bigger. So what is this gonna do? Let's click graph. The only thing this is going to do is going to vertically stretch, right? So let me actually zoom fit so we can see the entire thing. No, I don't like how this looks like. Zoom, standard, and I'm just going to do zoom, simply zoom out a few times. I'm going to do zoom out again. Let me do zoom in again. Oops. I'm going to do zoom in. And then another zoom in, I guess. Here we go. So we get a graph that is vertically stretched. Okay, I'm going to change that that 3 for a 2 and see what happens. So it now gets a little bit vertically shrink the minute I do a smaller one. Well, I'm going to type the 1. But the thing is, the position of the x-intercept is not going to get affected. The x-intercepts are still the same. Let me change that to 1/2. See what we get. It got shrank vertically. See? Zooms. Standard. I'm gonna do the original zoom, and then look at the position of the x-intercepts. They are still the same regardless of the value of a. So when it comes to coming up with a function like this, a is not gonna matter when it comes to the x-intercepts. Now they're asking us for a polynomial function, which means we need to expand this. I'm going to use the back side of the page because I ran out of space here. So let's see. So I got f of x equals, so what I'm going to do here is to FOIL this. X squared minus 2x, 3x minus 6. X squared minus 2x and what was it? 3x minus 6. And that times x minus 5. So I'm going to simplify this one first. X squared plus 1x plus x minus 6 equals, times x minus 5. All right? And then I'm going to do the same again. I'm going to FOIL x squared times x squared times a negative 5. So x cubed minus 5x squared, and then x times x times a negative 5 plus x squared minus 5x, and last but not least, negative 6 times x, negative 6 times negative 5, that's going to give us negative 6x plus 30. Alright, now we're not done yet. We need to combine like terms, squares with squares. I use 2 bars for squares and 1 bar for linear terms, that is terms that have an exponent of 1. So my final function f of x, a polynomial function, will be x cubed minus 4x squared minus 11x plus 30. I'm going to graph this function just to show you that whether you use the polynomial version or the factor version, you should get the exact same graph. So I'm going to go ahead. X cubed minus 4x squared minus 11x plus 30, and hit graph. So first it's going to graph the factored one, and now it's graphing the other one. It's actually overlapping. Hopefully it was easy to see, but it's actually overlapping because it's the same graph. Alright, so that's what they ask us for a polynomial function. Yes, first we write it in factor form with the zeros, and then at the end we expand all this to get the polynomial. Alright, let's move on and find out what's next. Okay, so it happens like in the example that we did before, right here. Remember the one that in which I have a repeated power? I had a repeated factor because I had a higher power of the same factor. So, and this is what the next definition is about. So, one of the factors x minus r may occur more than once, and in those cases we call it a repeated zero or a multiple zero of the function f. Okay, so the definition, more formal in a more fancy language, it's this: if x minus rm is a factor, but x minus rm plus 1 is not a factor, with this we're saying that m is the highest power of that zero in particular. Then we say that r, whatever that value is, it's called a zero of multiplicity m of f. In particular, going back to the example I have in the previous page, this 0 x minus 3, because we have it twice. This is multiplicity 1, and this one, because I only had it once, multiplicity 2, because this was not repeated. This is multiplicity 1. So multiplicity 2 because there's 2 of them, multiplicity 1 because there's only 1 of them. If I had this x minus 3 to the 5th power, then this would be a multiplicity 5. If I had x plus 1 to the 7th power, then it would have been a multiplicity 7. Alright, let's do an example. Identify the zeros and their multiplicities. So in this case, we are going to have the following. Keep in mind that x minus 3 will have r equals to 3. X plus 4 will have an r2 of negative 4, and x plus 1/7 will have an r 3 of negative 1/7. Okay, so we change the sign of these values when we state the zeros, and we change the sign of the number when we write it in factor form. Now, R1 equals 3, and that's one of the zeros, and the multiplicity is 1 because I have an invisible 1 power. R2 equals negative 4 is of multiplicity two, because 2 is the power of it. And R3 equals negative 1/7 is of multiplicity 4, because the highest power is 4. All right. Now let's look at another example. So let's see. So in the next example, let's form a polynomial whose real zeros are given and their degree, Okay, so they're giving us that one of the zeros is negative 2 with a multiplicity 2. And the other piece of information is that the other zero is 4 of multiplicity 1, and the overall degree is 3. Alright, and if you think about it, multiplicity 2 will give us a second degree polynomial, and multiplicity 1 is going to give us a first degree polynomial. When we multiply a first degree polynomial times a second degree polynomial, observe that the highest powers of each multiply each other, and when we do that, those powers, those exponents add up together. So in this case we are going to add 2 plus 1, which must be the degree 3. For example, if I told you instead, I'll give you 0, negative 2 of multiplicity 2 and 4 of multiplicity 1, but I want a degree 5. Well, in that case it wouldn't make sense. That wouldn't be such polynomial because I only have multiplicity 2 and multiplicity 1. It's not enough to to provide a degree 5, so there's no way. So everything should be consistent with what is given and with what is expected when it comes to these types of questions. So let's see. So again, answers will vary depending on the choice of the leading coefficient. All right. So for example, okay, so f of x, it's going to be the 0 is negative 2, then the factor is x minus negative 2 of multiplicity 2, and then 4 is the 0, that is x minus 2. I mean x minus 4, and in this case to the first power we don't need to write that 1. Alright, let me simplify this. I'm gonna get x plus 2 squared times x minus 4, and in this case keep in mind that a, again, that's the reason for which answers may vary because of due to our choice of a. So in this case I will choose a equals 3. Don't be afraid to have a big number, that's fine. So I'm gonna have f of x equals 3, and I'm gonna expand this. Well, first I'm gonna have it this way, x plus 2 squared times x minus 4. Alright, so I'm gonna expand the binomial first. 3 times x squared plus 4x plus 4 times x minus 4, and then I'm gonna have 3 times multiplying x times x, that's gonna be x cubed, x times negative 4, that's a negative 4x squared. 4x times x, and 4x times negative 4, that's going to be 4x squared. Oh, these are going to get cancelled. And 4 times negative 4 is negative 16x. And last but not least, 4 times x, 4 times negative 4. That's plus 4x minus 16. And I'm going to combine or close parentheses and combine like terms inside. So squares with squares. In fact, these dudes cancel here. These guys cancel out. And first powers with first powers, I'm going to get the following. I'm going to get f of x equals 3 times x cubed. No quadratic terms. Minus 16. Not minus 6. Okay, minus 16 plus 4, that's negative 12. Alright, negative 12x and minus 16. And then multiply everything by 3. Which in this case will be 3x cubed minus 3 times 12 is that 36 x, and 3 times negative 16, negative 48. Final answer. Okay, again, we're looking for a polynomial, not only for the factor form. So when you do your homework, if you give this form to the MyMathLab command, it's gonna mark you wrong, and well, in fact, it's gonna tell you, although your answer is correct, it's not in the required form, which is this, the polynomial form, not the factor form. Now find the polynomial function whose zeros are negative 2, 0, and 2, and whose graph passes through the point negative 4, 16. Now that's an interesting problem this time, because in this case we are not just going to choose our favorite value of a. In this case we are given a particular point, a point that actually lives in the function that we are trying to come up with, that we want to obtain the polynomial. So in this case, this is what we do. So first of all, f of x, a times x minus r1, x minus r2, x minus r3. So what are the zeros? r1 is negative 2, r2 is 0, and r3 is 2. Simplifying this, we get f of x equals a times x plus 2 times simply x and x minus 2. I'm going to rearrange this in a simpler form. Ax times x plus 2, x minus 2. And in this case, instead of foiling this, you might want to recall that this has the form of a plus b times a minus b, which is the factor form of a difference of squares. So you might want to just do that instead of foiling. However, if you want to spend some time foiling, it's fine. That's going to be ax times x squared minus 4, which will be ax cubed minus 4 ax. Alright, so in this case we are going to look for a given this point, given that x equals negative 4 and y equals 16, which is the same as f of x. So replace 16 with f of x and plug in negative 4 wherever you see the letter x. So this will be a times something cubed minus 4 times a times something, which in which the something is x equals -4. So -4 squared, that's going to give us 4 squared 16 times 4, that's a -64a. And then negative times a negative is positive. 4 times 4, 16, 16a. Combining these two terms, we get the following. We get -64 plus 16. This is going to get -48. A equals 16. Dividing both sides by -48, we get that A equals 16 goes into 48, 1/3. Okay, because 16 times 3 equals 48. So now our final answer it's going to be this function, or rather this function, that's correct. F of x equals actually -1/3. -1/3 x cubed minus 4 times 1/3, 4 times -1/3 x. Simplifying this, we get -1/3 x cubed plus 4/3 of x. All right. So that's what we get for this exercise. Let's see what's next. All right, so now let's move on to the multiplicity and see what's the effect on the graph of a function. So the multiplicity over real zero determines whether the graph crosses or touches the x-axis at whatever zero. So if the zero is of even multiplicity, and in this case 0 of even multiplicity will only touch the x-axis at that value of the 0. Otherwise, if 0 is of odd multiplicity, then f is going to cross the x-axis at that value of r. Okay. Now, turning points. So graphs are, well, the polynomial graphs are going to have, different shapes in different regions of, or in different domains. In some domains are going to go down, up, etc. That's going to produce turning points. Those turning points are going to be those points in which, okay, let me draw this. So notice every time I hit a max, that's one turning point, that's another, etc. I'm going to go up, I get a maximum, that's a turning point. To go down, I get to the minimum. To go up, that's another turning point. And same here. And the number of turning points, it's given by the value of the highest degree, or by the degree of the polynomial. For example, if we have a function f whose degree is n, then the graph is going to have not exactly n-1, but at most n-1 turning points. That means that, for example, if I have a polynomial of degree 2, do you remember the polynomial of degree 2 is it's a parabola. Okay, let me give that example right here. It's a parabola that opens up or down depending on the sign of the leading coefficient. Okay, the degree is 2, but how many turning points do you see? Do you see only one? A polynomial of third degree will have then one less turning point than it has, than its degree. So it's going to have 2 turning points. We're going to see a little bit more about that. Now, again, the end behavior, that's one of the most important aspects when it comes to polynomial functions. Okay, again, this is the general form as we already did at the beginning of the section. However, the term that dictates the behavior of the polynomial is actually the leading term. Okay, it's the leading term. So for example, when we're gonna have 4 cases. I'm gonna go with the even degrees. When the degree is even, f of x is gonna go all the way to positive infinity as we go to x equals positive infinity, and when we move back to negative infinity, f of x is still gonna go to positive infinity. And this happens when the leading term is a sub n is greater than 0. That is, the leading coefficient is a positive number. The same idea for this, but now we are going to have a leading coefficient negative. Remember from the previous section, reflections, having a negative leading coefficient will reflect the graph about the x-axis. In other words, it's going to flip the graph upside down. Alright, so in this case, if we move to x all the way to positive infinity, it's going to go down to negative infinity. If we go back to negative infinity, the y value is going to go down to negative infinity. Now let's look at the odd cases. For an odd case, and the leading coefficient to be positive. Okay, leading coefficient positive. What's going to happen here? Well, as we move to positive infinity, f of x reaches the value of positive infinity as well. However, in this case, as we mentioned earlier in this section, earlier in this video, as we move back to negative infinity, this goes down to negative infinity. You can see that here in the description. Now, keep odd degree, but now in this case leading coefficient is negative, so these are going to be flipped. So in this case, we move to positive infinity in the x direction, y is going to go to negative infinity, and if we go back to negative infinity, y is going to go to positive infinity. This is going to be very important when it comes to sketching graphs of polynomials by given some information. So having an understanding of the end behavior is going to be very, very crucial to see, to determine how is the graph going to look like. So let's look at an example. We are given this function, this polynomial function. Well, it's already in the factor form. Number 1, list each real 0 and its multiplicity. So in this case, R1 is -4 and R2 is -3. Those are the 2 real zeros. This one has a multiplicity of 2 because that's its power 2. On the other hand, R2 equals -3. It has a multiplicity of 3 because 3 is the highest power of it. Alright? Now, in this case, we are going to determine whether let's see. Okay. We're going to determine whether at each 0 will the graph cross or touch the x-axis. So R1, which is -4, has even multiplicity. For that reason, let's go up here. Even multiplicity is going to touch the x-axis. Therefore, f touches the x-axis at x equals -4. On the other hand, R2, which is -3, has an odd multiplicity. Therefore, f, according to the oddness here, odd multiplicity crosses the x-axis. At x equals -3. And these are going to be one of those ideas that we are going to put together when it comes to describe and analyze polynomial functions. Let's see what's next over here. Determine the maximum number of turning points on the graph. Okay, first of all, what kind of information do we need for that? We need to know what the degree is. So let's see. In this case, well, I'm not going to expand this polynomial. In this case, notice this is degree 2 plus degree 3. The overall degree, we're going to have a bunch of terms. We add the 2 degrees, the degree is 5. Okay, so we have a 5th degree polynomial here. And it's going to be n minus 1 turning points. That is 5 minus 1, which equals 4 turning points. Determine the end behavior of the power function that the graph of f resembles for larger values of absolute value of x. All right, what are we going to do here? First of all, let me rewrite the function that we were given. So in this case is 4 x plus 4 to the second power times x plus 3 cubed. Okay, so in this case, I'm going to pretend that I don't have the plus 4, and I'm also going to pretend that I don't have this plus 3. Okay, I'm going to pretend I don't have those. So this is going to behave like approximately 4x squared times x cubed, which ultimately is 4x to the 5th power. So that's going to be the power function that relate this polynomial function, and this is what is going to determine the end behavior of it. So as x approaches infinity, we're going to have that f of x approaches also infinity, and for negative values of x, we're going to have also positive values of x, which is what we have here from the end behavior. Okay, positive values of x, positive values of y. Negative values of x, still positive values of y. That's the symmetry about the y-axis, or the fact that it's an even function. If we wait a minute, no, this is an odd. Never mind. This is negative. It is also negative. Never mind. It was an odd. I was looking at the even for some reason. So it's going to be this third case right here. Positive values of x, positive values of y. Negative values of x and negative values of y. That's all this chart reduces to. In summary, negative values of x, positive values of y. Positive values of x, positive values of y. Negative leading coefficient for both positive and negative values of x, we get both negative values of y. All right. Okay, let's look at example 9. For example 9, we're given a series of graphs. We're given a few graphs, and they're asking us to determine which of them are possibly the graphs of a polynomial or not. All right. So how are we going to determine that? Well, so first of all, one thing I didn't mention at the beginning of the video, because I wanted to wait until I get to this point, is that let me find the information first here. Let me retrieve it. So let me go back to the very first page. All right. Let me go to the first page and add a little bit more to our definition of a polynomial function. So, and this is the most important part of it. So, a polynomial function must be continuous and smooth for all x in the real numbers, for all real numbers. That is, no gaps, no asymptotes, no holes, and no cusps. What is a cusp? A cusp is a sharp corner. We're gonna find out how those are gonna look like over here. All right, so let's see. So letter A. So if we follow the definition well, look at this. We have some trouble here. We're in trouble here. Do you see why? Well, if you say because of the gaps, well, that is correct. We have a gap here. At this gap, the function is not continuous. Suppose you're walking along this function. What do you have to do in order to keep going? You will have to jump, and you run the risk of falling into this hole. So it's no good. So this is not a polynomial. All right. Now, what about letter B? Letter B, if we walk along the graph, well, it's smooth, clearly smooth, and it's continuous. So in this case, it is the graph of a polynomial. So for those that are, list the real zeros and state the least degree of the polynomial. So in this case, one of the zeros, one of them is -2, the other 0 is 1, and the other 0 is 2. Okay. Now let's look at letter C. If we walk along this graph, well, observe the cusp here, the sharp corner. Okay. Gap. Cusp or sharp corner. So for this reason, this is not a polynomial function. Okay. In fact, you could describe this using a piecewise defined function, and I think it would be x squared minus 4, negative x squared minus 4, and some crazy line over here. Well, it's not part. Doing a piecewise function is not the objective, but I mean, it's a good way to relate this with what we already did. Now let's look at the last of them. Well, so number 1, if we walk along this graph, it's smooth and nicely continuous. Okay, so yes, this is. Now, how many zeros? We have 1 and 2 zeros. One of the zeros is -3, and the other 0 is 1. Okay, they're also asking us for the degree of the polynomial. Well, in this case, we have 1, 2, 3, so the degree is 3. For this last one, we need to be very, very careful because we have 2 zeros. So you may think, well, that might be a parabola, but well, look at the graph. The graph doesn't have the shape of a parabola. In fact, it looks weird. So in this case, we cannot see that the degree. We cannot say that the degree is 2 because the zeros are 2. All right. So we need to we need to look at this graph more closely. Okay, what are other properties of polynomial functions besides the zeros and the degree? Now, what about looking at the graph? If you're thinking the number of turning points, then you are correct, because we have one turning point here, then we have another turning point here, and another turning point there. How many turning points do we have? We have 3 turning points, which means that we have a degree of 4. Remember, the number of turning points is 1 less than the degree. All right? Let's look at another example. Which of the graphs in the figure below could be the graph of f of x equals x to the 4th plus 5x cubed plus 5x squared minus 5x minus 6? All right, so in this case, this is not what we're going to do. You might be thinking, oh, I'm going to plug in values from, say, x equals -4, -2, -1, -4, -3, -2, -1, 0, 1, 2, 3, and 4. Well, yes, good luck. It's going to take you forever to do that and then compare with these graphs. All right? That's not what we are going to do. What we are going to do in this case is use what we have learned of the properties of polynomials in order to come up with the most suitable either A, B, C, or D. Okay, so let's see what are the pieces of information that we can get from here. Okay, so from here we can get that the degree is 4, which means it's going to have 3 turning points. That's what we are going to obtain, 3 turning points. What other piece of information do we have? Well, intercept. Well, potentially for zeros. Potentially, right? Because again, it could have a maximum of zeros as the degree, which is 4. Okay, what are those zeros? So in order to get the zeros, we will need to set this polynomial equal to 0 and then solve the equation. However, we do not have at this point a tool to find x-intercepts of quartic polynomials like this one. We could do it if we had the second degree polynomial. Well, factor it out. If it works, then nice, it works. Third degree, well, factor by grouping, hopefully it works, and there you go. However, for 4th degree, well, that's going to be the next section, the rational root theorem, which is what we're going to do we're going to do soon. So in this case, we don't know that yet. All right. However, we can find out what y-intercept is. The y-intercept is obtained from plugging in 0 to x. 0 to the 4 plus 5 times 0 cubed. That's going to be 0 plus 0 minus 5 times 0 minus 6. So the y-intercept is 0 minus 6. So this graph is going to cross the y-axis below in the negative region. So let's gather all this information and compare all these 4 graphs with that information. So number 1, let's see. For number 1, what are we gonna have? Okay, let's see. We have 3 turning points. We have 4 potential zeros. Okay, this graph has 4 zeros. That could be a good possibility. However, look at the y-intercept. The y-intercept is negative, and in this case the y-intercept is positive. So right away we can cross out this possibility. It can't be that one. Okay, what else do we have? let's see the graph of B. The graph of B has 1, 2, 3, 4 zeros, and C also has 1, 2, 3, 4 zeros, correct? And both of them have a negative y-intercept. So it could be between these two. However, we need to watch those graphs more closely. Okay, what about D? We are going to have also a negative y-intercept, and we are going to have also 1, 2, 3, 4 x-intercepts. However, look at the end behavior. This looks like an even degree power function with a negative coefficient, with a negative leading coefficient because of the direction of the y value. And in fact, if you look at the leading term, this is positive. Leading term. Okay? So in this case, that can't be. All right. Let's look between B and C. How many turning points does the graph has to have? 3 turning points. How many do we have here? 1, 2, 3. So far, so good. Now, how many do we have here? We have 1, 2, 3, 4, 5. That's too many turning points for only a degree 4. So goodbye. And this is the winner. This is the good one. Letter B. All right. And let's wrap up this section looking at one last exercise. So now given the graph of a polynomial function, use the smallest degree possible to create a polynomial function. So what do we need? How many zeros do we have? 1, 2, 3. Notice that in this case, at the 0, -2, at the 0 at x equals -2, the graph touches only. So that means that the multiplicity is even, which means it could be multiplicity 2, multiplicity 4, multiplicity 6, multiplicity 8, whatever, etc. But for this case, in this case, I mean these two cases, the graph crosses, so the multiplicity has to be odd. In other words, the multiplicity could be 3, could be 5, could be 7, could be 9, 11, 13, etc. However, they are asking us to, or actually multiplicity 1 in this case, because that's also an odd multiplicity. Use the smallest degree possible. The smallest degree will be obtained by choosing the smallest in this case. So multiplicity 1, multiplicity 1, multiplicity 2. So how many turning points? 3 turning points. That's 1 less than the degree, than the overall degree. So multiplicity, actually degree, not multiplicity. Multiplicity is for each individual 0. Degree is for the overall polynomial. The degree must be 4. So I'm going to have something like f of x equals a times x minus r1, x minus r2, and x minus r3. But wait a minute, that's not degree 4. So in this case, one of these zeros has to have an even multiplicity, like the first one, and in fact -2. So x minus x minus -2 squared, x minus 0, x plus 2 squared. So in this case, f of x, it's going to be x plus 2 squared times x times x plus 2. Alright. Well, actually, the zeros. No, this should be negative. Negative. Alright, never mind. My bad. Okay. So how are we going to simplify this? This one is going to take a good minute to solve. So let's see. F of x equals, I'm going to write this x after the ax, and instead of foiling this x plus 2, I'm going to write it as x plus 2 times itself, x plus 2, and times x minus 2. The reason for which I do that is because over here I'm going to have this so-called a plus b, a minus b. I mean, if you want to foil this, fine, you're good to go. However, I'm trying to simplify some of the work. Maybe not by much, but at least it's going to be something. Ax times x plus 2 times x squared minus 4. That's what we get when we have a plus b times a minus b. That's a squared minus b squared. And then f of x equals, this is going to be a, I'm going to save the a for the end this time. I'm going to keep it. That's going to be x squared plus 2x times x squared minus 4. F of x equals a times x squared times x squared times negative 4. X to the 4th minus 4x squared. And over here, 2x times x squared, 2x times negative 4. 2x cubed minus 8x. And I don't think I have any like terms. The only thing I'm going to do is write this using descending order of powers. So a times x to the 4 plus 2x cubed minus 4x squared minus 8x. Now I need to find what a is, and in this case we are not just going to choose our favorite value. We know that the function has the point negative 1 comma 6. The point negative 1 comma 6 is in f of x. So that means that we can plug in y equals 6 equals 8 times something to the 4th plus 2 times something cubed minus 4 times something squared minus 8 times something. And the something is negative 1, negative 1, negative 1, negative 1. Let's simplify this. So this is 6 equals 8 times negative 1 to the 4th power, that is an even power, turns into positive, plus negative 1 cubed, that's going to be negative actually, not positive, negative. Negative 1 times 2, that's negative 2. Now negative 1 squared, it's positive 1. But positive 1 times negative 4 is going to be negative 4. And then negative times negative, negative 8 times negative 1, that's going to be positive 8. So let's simplify this. 8 minus 4, that's going to give us 4. 4 minus 2 is going to give us 2. And 2 plus 1, it's going to be 3. 3a. Okay, let's do that again. 1. 8 take away 4, that's 4. 4 take away 2, that's 2. 2 add 1, that's a 3. And divide both sides by 3 to get a equals 2. So I'm going to go ahead and write a polynomial function with a new value of a. F of x equals 2 times x squared, x to the 4th rather, plus 2x cubed minus 4x squared minus 8x. And I'm going to distribute the 2 to every single term inside of the parentheses. F of x equals 2x to the 4th plus 2x to the 6th minus 8, plus 4 minus 8x. Wait a minute, what am I doing? I was multiplying the powers, so that's a 3 instead. Where's my... never mind. Okay, this is a 3, not a 6. 8x squared and negative 16x. Final answer, and we wrap up this section with this exercise. I'll see you on the next video.